So logistic growth is also super common in the real world. So if you Google logistic growth, actually a ton of cool things will pop up. It's something that you talk a lot about in science, and you may have heard of it before. But if I just think about it, like when I think about population growth, so like if let's say a bunny population is doubling, right? Like it's not going to double forever because that would not be sustainable. Like that just doesn't make sense, right? Eventually there's going to be some sort of population control. Like maybe there's more predators that eat the bunnies, or maybe there's a lack of grass, right? Or a lack of food for the bunnies. Like if there's that many bunnies, if there's billions and billions of bunnies on Earth, like they're eating all the food supply, like something is going to happen to level out this population growth, right? So that's when we get this shape over here that's like a flattening of this curve, okay? So why don't you sort of think about what you've been hearing in the news about flattening the curve for exponential growth, specifically with the coronavirus, right? So like, what does that mean to flatten the curve? Well, that's exactly what we're talking about here, right? So like if I look at this and I treat this like it's the coronavirus, if I start with, whatever, one case in China, and then all of a sudden this person interacts with 3 people and it then moves up here. Okay, they interact with 3 people, they interact with 3 people, they continue. But like that's not going to continue forever. If this growth rate continued forever, because exponential increases so quickly, like we would have no people on the planet within a matter of days, right? So eventually, like we take measures to flatten this curve. So if I think about it, like what are some things that we could do to flatten the curve? Well, we could do social distancing. We could do what we're doing right now, right? All of these things are going to keep this from just increasing forever and ever and ever. Our bodies also naturally develop immunities to things. We have certain like ways to fight this. We come up with our own medicines and testing, right? Like all of these things help slow down this curve and help change this exponential growth. So this is really important because it happens a lot. The one thing is we're not going to dive super deep into this. Actually, for all of the questions, I give you the equation. I just want you to sort of understand that like, while this is really helpful, like increasing exponentially and constantly, like, yes, this is true, but like it's gonna slow down at some point. It's gonna flatline when we're talking about things in the real world, because that's just what happens. Like Darwin talked about this. It's a lot of science. If you're studying that in your classes now, like we'll go through some more details on it. So just for now, I'm just going to give you the equations. I just want you to know that like this is what's happening when we're talking about flattening the curve. It's more of a logistic growth model here. It is exponential for a period of time, but then like that's not sustainable. That doesn't really make sense. So it's going to flatline out. So let's just look at what this happens. So like when this happens and how to use it. A disease begins to spread in a town of 20,000 people. After T days, the number of people who have been infected by the disease is modeled by the function below. Using the function, find the number of people infected after 10 days. Okay, so it's spreading. This disease is spreading. We know that when diseases spread, they spread exponentially because people interact with one another. Then they expose more people, then they expose, right? It's growing exponentially, but it's going to flatline because that's what happens when diseases spread. So I'm given this function, and I want to find the number of people infected after 10 days. Okay, so I'm just going to plug in a 10 for that T. So 20,000, you can already see that that's the initial amount on top. 1 plus 1150 E. Why is it E? Because it's continuous, right? Raised to the negative 0.95. And then T, so times time, which is 10 days. All right, you can plug this into your calculator, or I'm just going to come over here. It's a little easier for me to just plug it into Mathway. So if I'm over here on Mathway, I'm just going to sub in, make my fraction bar, and put 20,000 on top over 1 plus 1150. Come over here and find your little E button, and then raise it to the negative 0.95 times 10. And let's see what we get here. You can just press enter and it will give you your answer. So I have 18,415. We'll just round to the nearest whole number here. 18,415. Why would I round to the nearest whole number? Because I'm talking about people, right? So how many people? I can't have a half a person. So this would be about 18,415 people. All right, so let's look at the next one. The population P in millions of a country from 1850 to 2000 is modeled by the equation below, where T is the year since 1850. Find the population in 1920. Okay, so we're talking about population growth. Up here we're talking about diseases, right? So like population can grow exponentially for a period of time, but it's probably going to flatline out. It's either going to grow or decay. It's probably going to start to level off at some point or slow down. Otherwise, it wouldn't be sustainable. So if I look at number 8, I want to know in 1920, okay? So if this is years since 1850. So I just need to know how many years have gone by from 1850 to 1920, and that's going to be 70 years. Now I'm given all the other information here. My initial amount was 135 million. We can just use, it says in million, so I can just use 135 over 1 plus 58e to the negative 0.025 times 70. Okay, and I'm going to plug that over here. So same thing, I'm going to use the fraction bar. And then I'm going to do 135 on top over 1 plus 58e to the negative 0.025 times 70 years. And that is going to give me, I hate you, sponsored videos, 12.18 million or 12.19 million. Okay, so that's 12.19 million people. And this one you can't have a decimal because it represents millions. I could have 12.19 million people. That's fine. You can round to 12 million if you'd like. But 12.19 million would be the most accurate answer here. Okay, so go ahead and try these problems. So there's logistic growth on page 11 as well. The last two are just logistic. And like I said, I give you the equation. I just want you to understand that like I would be doing a disservice if I only taught you E in continuous growth without also saying that like, but actually in the real world, it's still continuous. It still has E, but it's probably going to flatline at some point, which is super helpful when thinking about the coronavirus that we've been talking a ton about. And also you'll feel super smart when people try to talk about flattening the curve. You can just be like, actually, do you even know what you're talking about? And I bet they don't because they probably didn't pay attention in their pre-calc class. All right, have a great rest of your day. Bye.